All right. Very good morning to all of you. Today, I would like to continue and give some more information on the principal component analysis we discussed last time, before moving on to nonlinear methods for dimension reduction. And you heard me preach about proper spelling last time, okay? All right. So, who amongst you has heard about the singular value decomposition? Okay, keep your fingers up. And now everybody, or keep them up. And now everybody who's not a physicist, put them down. Yes, okay, so early in the morning. Okay. No, this is my personal statistics. So singular value decomposition is important, and I think it's a bit under-taught in physics. Okay, so better? Yeah, okay. Good. So another way of looking at PCA is in terms of the singular value decomposition. SVD for short. And it says that for any matrix, real or complex, for any matrix A, there exists a decomposition in terms of three matrices U, S, and V transpose, such that U transpose U is the identity matrix, V transpose V is the identity matrix. So if A is P by N, then this here would be P by P, and this here. In this example here, I'm assuming that N is larger than P in what follows. So U transpose U, that would be a p-dimensional identity matrix. V transpose V would also be, in this case, a p-dimensional identity matrix. But I can also write it the other way around. I can say V transpose is an n-dimensional identity matrix. And S is a diagonal matrix with elements, so-called singular values, sigma 1 larger than sigma 2, and so on, up to some sigma, in our case, if P is smaller than N, up to sigma P. All right, and now these have names. We have here these U's. They are called the left singular vectors. The V's are called the right singular vectors. And the S are called singular values. And this decomposition always exists. And if the singular values are distinct, if we have no degeneracy, it's also unique. All right. And now if we have this decomposition, then we can look at the principal component analysis problem we had last time. So last time we wrote that x transpose times the first principal component that we were looking for, w equals lambda times w. And this was the eigenvalue, this was the eigenvector. And now if we use this decomposition here, then x transpose would be u as v transpose, v as transpose u transpose. But we required that this is the identity matrix. So this is just u, and this is a diagonal matrix, so S is the same as S transpose. So we have, I'm writing S squared here times U transpose. And okay. And this is X transpose. And now I can multiply, for example, from the right, and then I see that US squared equals X transpose U. And so here we already have our eigenvalues and eigenvectors. Yeah? So in particular, I can say that U is a matrix composed of column vectors. I'm here calling them U1, U2, and so on, up to UP. And so what we see here are many eigenvalues and eigenvectors at the same time. Yeah? In particular, I could also say that, for example, U1 times, U1 times S squared. Okay, here I'm just taking the first singular value. So sigma 1 squared is X transpose times U1. And so this would be the largest eigenvalue of X transpose. And that would be the corresponding eigenvector pertaining to the largest eigenvalue. Good, and now what does this do to a matrix? Instead of matrix X, instead of matrix A, I'm now writing here matrix X. Equals U as V transpose. We can think of it as follows. This is like a sum of rank 1 contributions. So sigma 1, the first singular value, times U1 times V1 transpose plus, I need more space, plus sigma 2, U2, V2 transpose, plus it goes on. And I'm giving a more graphical description here. So let's say on the left-hand side, we have this matrix X. And I'm now saying that this is sigma 1 times a single column vector times a single row vector. Yeah, so outer product of two vectors, this is a rank 1 contribution, weighted by sigma 1. And then I'm taking here another rank 1 contribution. And so on. So this here is U1, this is V1 transpose, this is U2, this is V2 transpose, and so on. And if this was my original P by N matrix X of observations, then what we see is that this here corresponds to the first principal component. And these here are my data projected onto the first principal component. So in the language of PCA, these are also called scores. This is the second principal component. These are the scores or projections onto my second principal component, and so on. So what you see is that I build up my matrix, or I build up my approximation to the original set of observations dimension by dimension. And in particular, I can also truncate this. So I can say that I'm using, for example, just the first 3 principal components. I have this tiny diagonal matrix here, which has mostly zeros, but has a few singular values. All right, and actually the scores, what we call scores, are the right singular values times sigma 1, excuse me, times sigma 2, and so on. Because, yeah, the principal components are normalized, and then the rest of the information is in the scores. Okay, so what we have now, this is a matrix. This was P by n. This one is also P by n, but in this particular example, this only has rank 3. So what we have, if we use the first 3 left and right singular values, or vectors, if we use the first 3, we have a rank 3 approximation to the original data. And it's the best possible approximation in the sense of the squared Frobenius norm. So the language of singular value decomposition, this is called the Eckart-Young Theorem. But it's really the same thing as what happens in principal components. Okay, bringing this together with a picture again. So last time we had plots of, some points that were centered around the mean. So altogether, these make up my matrix X. And then we were finding here the first principal component, which best approximates my data. And then orthogonal to that, and I can, if I wish, approximate my original observations in terms of their projection onto this principal component. Yeah, so if this here is observation xi, then that would be the score of xi along the first principal component. This coordinate here is xi transpose. Last time we wrote w. Today I'm writing u1, u2, and so on. But if I do want to approximate my data better, then I can use, in addition, the projections along the second principal component, which must be orthogonal to the first one, and again, best approximate the data in that remaining subspace after I have projected out the first principal component. Okay, and now how much does each of these components contribute? We can look at the amount of variance explained. How much does each principal component contribute to this approximation? Well, we can, so last time somebody came in the break and asked this formula x transpose is this not just the empirical estimator for the covariance matrix? And yes, it is. Yeah? So there is something called the scatter matrix, which is 1 over n times x transpose. And this is an empirical estimator of the covariance matrix. If the data has zero mean, yeah? So on-centered data. And now we can ask again, how much does each of the components contribute? And then we use the same formulation we had up there. Yeah? So the scatter matrix, this is 1 over n u s squared u transpose. And I was arguing that here these singular values, these are orthonormal, those are orthonormal. So these singular values tell us how much each of the dimensions contributes to the approximation. And so what we see here, if we again draw this kind of picture, which now would be symmetric, because x transpose as a whole, this thing is a p by p matrix. So if we draw this kind of picture, then we see that each dimension contributes singular valued squared. So how much does each principal component contribute to the approximation? And the answer is that the ith principal component contributes sigma I squared to the variance. And the squared singular values we have seen contribute to the eigenvalues, or correspond to the eigenvalues. And then at the beginning of last lecture, I was making an obscure remark, and I was babbling about something like a plot, where we ask how much does each principal component contribute. So I can now label this with amount of variance explained. And here I can label this with the index of the principal component. And because the singular values are sorted, this is always descending, or the most extreme thing I can get is that two adjacent values are the same. But usually I see some kind of exponential decay here. And last time I was arguing the example with the faces. So if we do principal component analysis on the space of faces, and principal component analysis is so fundamental that it has been reinvented really literally, I think, in every field of science, and everybody has given it a name of their own. So in the field of computer vision, this would be called eigenfaces rather than principal components, okay? But we always see this kind of exponential behavior. And in English, this is called a Scree plot. And Scree is not a word that I knew outside of machine learning. It just means, if you have a cliff and you have the sea, let's say this is the cliff of Dover, and then if you wait a million years, lots of pebbles falling down, and then eventually, you have this scree, this sort of hill of loose pebbles that looks like so. And this is why somebody has called it Scree plot, and the name has stuck. Okay, so this tells us how much of the variance is explained by each of the principal components, and this is an overestimate, or let's say this is a conservative estimate of intrinsic dimensionality. And why do I say a conservative estimate? Because if my data For example, if I have two-dimensional data, which essentially lies on a one-dimensional manifold, maybe this is what my data looks like in the 2D space. We would all agree that the data is in principle one-dimensional. I would say the intrinsic dimensionality here is 1. But if I do principal component analysis on this, I will still find a first principal component and a second principal component, and we have significant variance along both. Yeah, so in this sense, it is a conservative estimate or an overestimate of the intrinsic dimensionality that we get when we make this kind of plot. Or if you think of the surface of a sphere, the surface of a sphere, many of us would argue is intrinsically two-dimensional. But if I do a principal component analysis of this, I will find 3 large eigenvalues. If it's a perfect sphere, they will be of the same magnitude. And in that sense, it's an overestimate. But still, these plots are trivial when they are two-dimensional. We can all see what's going on. But if your data is very high-dimensional, this does give you important clues. All right. So this was my postscript for principal component analysis. I also last time did not give you a reference, and I'm sorry about this. It is written in every book except the die-hard Bayesian ones, because it's not a Bayesian technique. And the book I recommended last time is by Hasty, Tipshirani, Friedman, and this is difficult to spell. I show you later on the projector what it's spelled, and I give you a link to a document where you find a link to the book. It's a very nice book, one amongst many which would explain principal component analysis. Okay, do you have any questions about this? Yeah. Okay, the question was, is there any reason why the Scree plot usually decays exponentially? And there are 2 reasons. One is that indeed the intrinsic dimensionality of the data is in most cases lower than the nominal one. And I gave the example of the faces. I was arguing a picture has 1,000,000 dimensions because it has 1,000,000 pixels. But the space of faces is, maybe 50-dimensional, maybe 100-dimensional. So that's one reason. And the other reason is interesting, and we will look at it in the exercises. Okay, more questions? All right, so principal component analysis, my summary of PCA would be that it's a useful first method to look at your data, which must be defined on the interval scale. Pay attention to, so don't forget to center your data if you implement it yourself. What if you forget centering your data? So let's say these are your observations. And then you can think about, if you forget to center your data, if you say your origin is here and these are my observations, what will your first principal component now explain as opposed to what it should explain? Yeah, I would argue this is what it should explain. Yeah, this is the linear subspace that approximates the data well. But instead, of course, you get something very different. Yeah, if you forget the centering here. Also, don't forget to remove the label column before you do PCA. Yeah, so usually you have this matrix X, And usually you have a vector of labels y, and sometimes they are stored in one single matrix, and you don't want to do PCA on both of them. However, you can use the labels after the fact. You can create your principal component plot, and then you can show the labels afterwards to look at the distribution of things. Yeah, I think that's good enough. So much for PCA. And next, I want to revisit this question of, so for the projection, I was talking about having a spring here. And this corresponds to harmonic potential, and it gives us a unique solution, but it's very sensitive to outliers. So while I wipe the boards, you can start thinking about what happens if this observation lies not here, but if the observation lies here, or in the next room downstairs. Feel free to discuss with your neighbor. Huh? All right. So what did you find out? If the point goes further and further, what will it do to my principal component estimate? Any suggestion? Do you have one? No? Yeah? Yeah, so you propose a solution, but let's talk about the problem first. What is the problem? So if one observation is way out there, yeah?
If you have a median, it's not that much
Yeah, very good. Yeah, so if we have these harmonic springs, the force the spring exerts grows with the distance, and as the point, it sometimes happens, there is a mistake, a problem with the sensor, or there is some mistake in the data transmission or whatever, and you have observations which are way out there, and if they're way out there, they have an undue influence on the overall result, so they will pull the first principal component towards them, and you will not do justice to the rest of the data. Okay, so there is the problem, and you already proposed one solution. Yeah? And let's look at ways of quantifying the problem first, and then we can study a family of possible solutions and look at the problems they have. So this field of study is called robust statistics. Where robustness is robustness with respect to outliers. And in particular, what we are looking at are so-called M-estimators of location. So we can have many different statistical estimators for many different kinds of quantities. But the simplest one is always location, yeah? And this is what we're looking at now. And there is an empirical way of studying the impact of an outlier. That's the empirical influence function of some sample I. And formally, this empirical influence function, it depends on the location that we move our sample to, that's the location X, and then it depends on the estimator. Okay. So this here is some estimator. And then we have some training sample. How do I do a script X? Okay, this is the entire set of samples. Okay, and it's defined as follows. So it is n times the estimate that we get if we replace the ith sample by putting it at position X. So this is if we move ith sample to this position X minus what the estimator would look like if we had not changed anything. So if we had just used the original training sample. Okay, people on the very right, you lose the right. I'm sorry. Okay. Good. And this is the empirical influence function, and yeah, it depends on the sample. It depends on the estimator. And then there is a limit of it. So it's just called influence function, not empirical. And this similarly depends on a location where we move a particular sample to, and it depends on the estimator, and it depends on some distribution F. So this is the distribution. It's like an infinitely large data set. The distribution that the samples are drawn from. And now we look at this limit of following. On the one hand, the estimator, which is evaluated by admixing a small amount t, which goes to 0 from the positive side. We add a little bit of probability mass at location x to our distribution, which we diminish by a fraction of mass small t. Okay, I'm turning to the next line so people on the right-hand side can read. Okay, so this is the limiting case for infinitely large training samples. And now, so this is a formal way of describing what's happening. And now we will look at a couple of estimators and evaluate these functions for those estimators. So up there I wrote M estimator, and M estimator is short for maximum likelihood estimators. Or at least they have been derived from maximum likelihood estimators. Also sometimes abbreviated as MLE. And such a maximum likelihood estimator says we are looking for the parameter, in this case our location estimate mu, which maximizes the likelihood. So we have a product over all the samples in our training set, and then we have some likelihood, which I'm here calling f, of the ith observation under this location parameter mu, using some parametric model. And instead of the likelihood, it is often numerically more convenient to use the negative log likelihood. So I can equivalently look for the minimizer of, when I take the logarithm, here the product turns into a sum. Minus the log of f xi given mu. So this here would be the negative log likelihood. And this negative log likelihood is used so often that it gets an abbreviation of its own. In this particular literature, this is often abbreviated with a rho. Yeah, so, and now we can create a table of popular estimators. Namely, we characterize them in terms of their likelihood. We characterize them in terms of their negative log likelihood. Or sometimes this is called the cost. Sometimes this is called the loss. And if we want to give it a physical interpretation, we would call it the potential. And then there is the influence function. Sorry, there's some feedback here. Or it might be called the score. Or in our physical interpretation, if one is the potential, this would be the force. So we have the likelihood f we have this negative log likelihood rho, and the influence function is defined as the derivative of rho with respect to the location parameter, with respect to the sample position, sorry. Okay. And now the prototypical one is to assume that our data has a Gaussian distribution. So here this would be proportional to that. And if we now take the negative log likelihood, what we find is just a parabola, and the influence function is a straight line, which goes through the origin ideally. So the further we move our point out, the stronger its influence. And when we were discussing earlier what is the problem now with PCA and outliers, then we used implicitly this kind of loss function. And moving an outlier further and further out meant that it exerted greater and greater force, or had larger and larger impact on our estimate. So we want something more robust. And you already proposed a solution. You said, let's use the median. And the median is associated with an L1 loss. So the absolute value of x minus mu. And its influence function looks like so. So it only matters if a sample lies to the right or to the left of our estimate, but not by how far. And if we want to give this a probabilistic interpretation, we could say that this comes from e to the minus x minus mu. So a two-sided exponential distribution, or also called a Laplace distribution. So this here was the normal, or the Gaussian. And this is the Laplace, or two-sided exponential. I give one last entry for this table, namely, what if we want to make this more robust still? So we have many choices of what this could look like near the origin, but one possibility would be to have it like a conventional, just like a parabola around the origin, but then have this taper off. And we could either have a hard kink here, or we can gradually, beyond some threshold, have this continue like a constant, for example. This includes a crucial new parameter, the bandwidth. And if we now look at its influence function, this one is interesting because around the origin, yes, it grows linearly, but then it tapers off, and at this beyond this threshold here, it's 0 and it remains 0. So in other words, outliers beyond the bandwidth have no influence whatsoever on our estimate. And this one does not really have any distribution associated with it because it is not normalized or not normalizable, but this is called the Tukey estimator, and is a really, well, frequently used and important one. Okay, and then there are many others, which I'm not going to put down in detail. For example, you could use a Cauchy distribution here. So you could say, let's do 1 over 1 plus x squared, and then you can see what those will look like. Okay, and after the break, we will study in one dimension first what the properties of these are. And yes, we will see that they are more robust, but we will also see that estimation is no longer possible in closed form for non-convex ones like the Tukey. Okay, and we have a 15-minute break.